Okay, hello everyone. We are going to do a working session talking about multicomputation, its theory and implementation. So first on our list here, we're talking about lazy data structures. Let's just understand what we're roughly talking about here. We're going to be talking about the concept of lazy data structures, and we're going to be talking about a quite separate topic, which is the granularization of pattern matching. Is that a fair statement? And these are not directly related topics. Is that true?
Well, they're related because we already discussed pattern matching, and my plan was to make this intermediate data structure lazy for the pattern matching, so that it returns a generator of matches.
Okay. Well, that seems like it's okay. I need to understand that. I don't necessarily understand that, but let's take a look here at this concept. So how many lazy functions do we think we want to have? I mean, is it lazy of everything, or is it just a specific set of lazy functions?
Well, at first I just implemented all the list functions as a sub-value for a specific lazy list, right?
Yeah, okay. Nick, have I sent you the list? What was it called? There was both a thing that Athena made, which is very similar to this, and also a thing that I made a while ago that had a few more functions in it. I'm not sure if I've sent that.
I don't think I've seen yours, but I've seen Athena's. Yeah.
Okay. Well, I should probably send that at some point then. But yeah.
Okay. So why are these not up values now?
Well, the thing that I realized that I want to actually achieve with this thing is not to work, because list functions, they not actually only work on lists, like they work on arbitrary heads.
Mm-hmm.
And I kind of wanted the same functionality for every head that has hold all attribute.
Okay, but we're not going to have a lazy version of each function. So the only way to do that would be to have some kind of a lazy headdress.
Oh yeah, my idea was also like have a lazy in the Parklet, like a lazy version for each list function. Also some kind of...
No. If we're going to have this as a serious thing that's actually integrated with the language, that's not something we can do.
I mean, I would just imagine. I don't think it's we already have stuff where, for example, part. If you give part a quantity array, it doesn't actually extract part. It runs some more. It does a more complicated indexing operation. I mean, the same way, I think that mapping over a cons object or something, it's fine if it doesn't literally map over that expression, if it does something more complicated.
Yeah. I mean, it becomes a single point of specialness, so to speak, that there's a special lazy structure that various functions respond to in a special way, just like, just like part extraction does something special with sparse array or something.
Yeah, but what if I want my own head that I want to make work with these lazy functions? It's like if I have a head that has hold all and I want to use map in a lazy way and select in a lazy way.
I'm not sure why you want to. I mean, like, so this is one of the things that was actually one of the useful products of Athena's project, was just that we try to think about other lazy data structures. And the basic conclusion was that it only made sense to do lazy data structures when they had analogous non-lazy data structures for which we already had a bunch of operations, right? That if we try to invent some other data structure with some weird shape that, we don't have operations that work on it. And so it doesn't really make a lot of sense. And so, I mean, I think that basically the only lazy data structures you're going to end up having are going to be things like lists, basically. In the case of Athena, we also have the trees, but you know what I mean? Like, I doubt there's going to be 100 other user-generated lazy things that are substantially different from just lazy lists.
And by the way, also, lazy graphs already a very complicated concept, because that involves this whole traversal order business and so on, if I'm not mistaken. Maybe not. Yeah.
Well, yeah. In a way, it kind of boils down to the generator that generates something. Maybe it's ages.
Right. But so the basic point is, people, one of the things we've learned is that in version 1, we were much bigger on the idea of functions that operate on arbitrary heads. But realistically, a lot of people just use lists for things. One finds oneself just using lists. And I tend to agree that we should build something that works for lists. And if we need to eventually have a general laziness wrapper that works for other expressions, we could do that too. But the concept that you have a raw expression and the operations then become lazy just doesn't seem like the right way around.
No, I don't know. I was just trying to, because now I have a specific case that I want to work with, this pattern matching. And for the pattern matching, I actually have two lazy heads that I want to treat differently. If I just, and it's going to be, it would be like much prettier if I just can use them instead of.
It's not going to be much prettier because you're going to have 3,000 functions with lazy variants of them. That's not prettier.
Well, it's I looked at it like analogous to parallel. Like we have parallelize that kind of just dispatches to whatever it finds and parallelizes it. We can have a similar thing here for lazy wrapper, and it's just lexically transfers a strict version of a code into a lazy one.
Well, but maybe two differences. I mean, so there are two parallel things. There's functions like there's parallelize and there's like parallel map. And the first thing is that things like parallel map have to be distinct because their inputs are the exact same as map. In this case, the inputs have they have some special head or something like that. So you can distinguish them. The other thing would be that I don't think parallelize has been particularly successful.
No, not. Nobody trusts it.
Right. And it also doesn't burrow in. I was surprised by this, but apparently parallelize only looks at the outermost level. So if you have f of map of blah, 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 and you run parallelize of it, it won't see the map. It just looks at the f and tries to parallelize that.
Well, right. that's just that's for Roman, that's an implementation limitation. But I don't think anybody trusts it. I don't.
Yeah. I think headdress would be better. But
parallelization is a heavy enough operation, at least in the current state of our system, before we get a parallelizing evaluator, that you're just going to want to say, oh, I'm it's a conscious act, so to speak. So let me just understand what the basic structure is here. So there's a concept of a lazy list, which would display I'm confused here. So you'd have a lazy list, and it might display with a few elements shown, and then the rest of it is just the symbolic version of the operations together with the generator. Is that correct?
Yeah, like the second line with primes example. Like the first one is just only a single one, and then some of the elements already evaluated. And the last one is just what is left of a generator for the next one.
Okay, hold on. So if we just had the lazy list concept, how would that work here? That would just say, what are the arguments to lazy list?
Well, it depends what lazy list is. It converting a strict version to a lazy one?
No, it's
the same as cons there, basically.
Right. You need constructors for it that can construct. Right. Just the function list is not the only way you create lists, right? And the function list, if we had something analogous for lazy list, presumably it would be, like you say, something that takes a finite list of arguments and turns them into a lazy list, but it's only finite. So you need to have constructors like lazy range or maybe lazy table, right? That can take infinities.
Well, in particular, lazy table would look like that. Lazy table is arguably like sum.
Lazy does not necessarily mean infinite, though. Like at least in the lazy list stuff I made before, it was critically did not have to be infinite.
Right, but so look at it compared to sum. Sort of the same kind of concept, isn't it?
Yeah. It
And
might
we
be
have
worth
less people there.
it might be worth making a distinction though between, I mean, again, I think that these things should have the exact same behavior as finite lists, except that they happen, you know, it happens that you can put infinity and it will still work. So
Yes.
I imagine that with something like a lazy table, you'd either want to be able to say, you know, I comma infinity, or you'd want to have a function with a different name from table that just has very similar behavior.
Well, I don't understand why table, you know, I squared I 1 to infinity doesn't just work. As in, why isn't that the thing? No. What I mean by that is it stays symbolic and it becomes a lazy list.
Well, that's a different kind of lazy list, though. I mean, again, this is one of the issues that we've had. I mean, this is why we don't have any kind of serious built-in lazy, you know, or sorry, infinite, you know, arrays, is that basically they're different kinds of lazy / infinite arrays that we want for different purposes. I mean, there's the Leonid style generators and streaming stuff. There's which is sort of good for sort of certain kinds of very programmery operations. There'd be some of those lazy array stuff we had previous summer schools where it's basically you have like, you know, a function where you give it a position and it tells you what the value is at that position. Right. That's useful for all kinds of like linear algebra stuff and more theoretical stuff. Then there's stuff like the cons lists, which are kind of more of a functional programming thing. It's kind of in between. And, you know, right. I don't think there's a single way that we'd want to do this.
All right. So what you're saying is there are list generators, e.g. table, range, etc. Array is a list generator. What other list generators are there?
There's a list.
There's a thing like repeat and clone in Haskell that repeat is just repeats one element infinitely and clone lists a finite list infinite times.
I'd say repeat is the same as table of, you know, x comma infinity.
Yeah, it sure is.
Nest list and nest while list.
Ah, yes, nest list is a great one. Fold list as well. Fold list can eat, you know, infinite things too.
Well, yeah, but it is not a primary generator.
Sure, okay. But nest list.
Fixed point list as well.
Yeah.
Right. So these are things that out of whole cloth, unlike fold list, which only takes
you start out with a list already.
Yes, right. So it could start with an infinite list. So I mean, just to be clear on this,
you could put map in the same category, like map over.
Sure. So I mean, in one of these might be range of infinity. And then we might be able to say fold list, you know, plus onto range of infinity. And that should generate, you know, the obvious squares. Okay. So there are list generators. So then there are list queriers. Of which things like part, well, I don't know what their query is. List transformations.
Yeah, transformations and extractors I think are different. But I think extractors on infinite lists are often not the most interesting things. I mean, there's some that you need, like arguably you need something like take that lets you make a, you know, finite version of one. Although I think the best way to do it is to have take do the, you know, take returns another infinite thing and you call normal on that to turn it into a, or sorry, returns another lazy thing, but which is finite, and you call normal to make it concrete. But that's a detail.
Probably, yes. Okay, list transformers, things like select.
Yeah. Fold, or like fold list, I guess.
Okay, listability. That's a very basic one. You know, we really have a cantorial issue of lining up the things. If we say one list plus another list, we have to know that we can line up the infinite elements.
Well, cons lists can only do finite. You know, there's another reason for you know, why the infinite list stuff is complicated, because there might be things, I mean, a bit like the implicit region, implicit set discussion, you know, where you have you know, more than what aleph 0 elements in your infinite list.
Yeah. Okay. So again, what do we think the basic design for this should be? Are we?
So what is the sorry, I don't have any context for this. I mean, is the context this to be a system thing, or is this going to be a useful packlet?
I think
You know,
I would like to see whether it can become a system thing. That's the question here. Maybe it can't.
I still sort of maintain that, at least without very careful naming or something, that there are too many different infinite array ideas for that you know, that only work for one of the like 4 applications, and so I question having a standard one.
Okay, but the other, you know, structure types, we already know they're lists, they're trees, and eventually they're graphs, which could be infinite.
Well, but I mean, there's arrays. How about, as opposed to like matrices, tensors, right? Which in general you can make from lists, but it's much, you know.
Yeah, but the question of whether they're ragged,
whether
or
it's
not.
natural, or right, whether it's, yes.
Okay.
I mean, as well as even more basic things like how you're representing the infinite data. Like, is it a, you know, for example, in lots of mathematical contexts, you know, you might have something where, oh, if you give me an index, I can give you the value at that index. I'll just put it into my formula here. That's not what this, you know, these cons lists do. It would be, you could probably do it, but it would be pretty painful. But yeah, just to use another example.
Okay.
Like if I want to index into the billionth position in a matrix specified like that, I'd much prefer it to be a matrix where, you know, it just queries the formula than a cons list that goes the whole way, which is just to say, you know, yeah, I mean, they're just different applications.
Right. Okay, so now this is your version here.
Yeah, this is kind of old, but I mean, this is probably, you know, and it probably doesn't have as many functions, but it's I'm sure it works in fundamentally the same way.
Cons is the basic function is cons here.
Yeah.
Why does it need that initial one?
So the first element is the value, and the second element is the rest of the values. So it's effectively a linked list. So that one is saying that the first element of this list is 1, and the rest of the elements are 1s.
Is this recursive definition a natural way to do this or not? Or is it better to have something which looks more like a, you know, a recurring decimal or a you know, would it be better? Go ahead.
I think this is it's natural that you're able to do this, but I think obviously if this were some sort of built-in thing, you'd probably want to do something like we said earlier with table of 1, infinity or something like that.
Well, fundamentally,
Like
argued that's the most natural way. And
which is the most natural way?
The recursion version. And then all the functions that generating lazy list is just doing recursion underneath it.
I am skeptical. I'm deeply skeptical of that. I think that there are many different kinds of recursion, and you have no idea what all the structures are, and there are no equivalence theorems for them.
Well, still,
the type of recursion is very simple.
It's like all the tables, all the fold lists, all the definitions of lazy functions, they defined using recursion.
Right. Which actually leads to some problems, because there's some dollar recursion limit things that I'm not sure you can really get around. It is for the top level
right, but
implementation.
I'm saying that I do not believe that giving people the idea that you can define an infinite data structure routinely by recursion is a good idea, because I think the only ones we're going to be able to deal with are ones that have been defined to be essentially very linear infinite structures, for example.
Right. I mean, I think like look at some of the later examples, because I think most of the examples I don't like. If we go up a little bit more, most of the examples I don't start by making a variable like that. It'll be something more like it. Sorry, if you go up a little bit, there's an example like, there's an infinite nest list, right? Where it's it's nest listing, and then I forgot, this is some, I think this is like the Babylonian method for computing square roots or something, which is not actually Babylonian, it's just called that. But then you see, you can query it, and yeah. But the point is, you don't actually. Sorry. The thing that says nest list of hash plus n over hash. It's near the top. I mean that would be an example.
That's an infinite. I see. That's an infinite nest list.
Right.
So do all of these operations like map? Do they always return a cons?
Yes. The only thing that the only way you can get something that's not a cons is basically by calling a normal.
See, I am much more of a believer. I do not believe in this recursion definition of things. I think, as I say, I think that I claim, and maybe James or somebody can, I claim you can construct one of these Paris Harrington sentences and God knows what else. You can make some kind of weird Hydra creature. You can do all kinds of things with that kind of recursion. It's extremely hard to untangle. And I don't think we should sign up to be able to do that. Am I wrong?
I'm not really sure what you mean. I mean,
well, because I claim, okay, let me give an example. If I did here. This weird thing, I'm pretty sure is definable quite easily by recursion. Oh, in fact, this is a recursive definition here.
What's your point? I mean,
my point is that you very quickly get into things that are undecidable by doing this, and that we should not.
I mean, but the whole language is undecidable. You'd hope.
Yeah, I realize that, but what I'm saying is that what we want to do is maintain things that are clean, like a linear loop, a thing that just keeps looping forever, and it's just one loop. I think we can deal with that. By the time we sign people up to be able to have arbitrary bubbling collections of loops, I think it's really hard.
So the point is that there isn't, though, because you can only have, it's always going to be some kind of, well, right. The recursion is very limited because it's just a 2-argument. Cons is, as a convention, is always a 2-argument thing.
No, I realize that.
So
that's
only
recursion is
chain
limited.
Of recursion.
Yes, I understand that. I'm arguing against setting these things up by saying x equals blah comma x. Because I think that's
sure. I mean that will work and it should work. But
for that particular case, but if I have 7 x's in there arranged in different ways, I have them interacting with a y and a z and so on, I'm pretty sure I can rather easily construct a very hard to untangle set of recursive functions.
No doubt. But I mean, this is you can already do that. I mean, that's sort of it's just, if the question is whether the convention should be that you should write things like that, then I would agree, probably not.
Yeah.
But
I think it's better to have an explicit thing.
Yeah, I mean, I think it's nicer to write something like cons range or whatever you want to call it.
Fine.
Than it is to
yeah, that's what I think. Than just to have the implicit definition where you essentially have to solve the equation to get the structure. All right, so what is it that we're talking about here? So you've already got something with this notion of lazy range.
Yeah, actually, in this notebook, I think it's called cons range. That lazy range was another thing I made that I was comparing it to.
Oh,
yes.
Okay, but so how many new primitives do you need in this way of doing it, where it's a data structure first way of setting things up?
mean, I think in this notebook, I only had, I think, one new function, which was the cons range function.
Well, you also have cons itself. I mean, this thing here.
Yeah. I'm talking about constructors for cons, right? For infinite lists. I think range was the only one, other than a kind of slightly bad repurposing of nest list, of a 2-argument nest list.
Mm-hmm. Okay, but the question, the hypothesis here is, I'm pushing back very hard against having a lazy version of all these different functions. And I'm much, my initial take is it's much better idea to have a single lazy list, lazy constructor, whatever it's called. I don't know.
Right. I mean, the point is just that you do need to have a different, function name when the inputs are going to be the same, like with range.
Yeah. Well, I don't understand. Range of infinity is the way that you get the thing that we're talking about here.
But you might want a finite. You might want a finite cons list. These things are not necessarily infinite. And I think it's important that they're not necessarily infinite, because it means you can do things like, you can run take of 100 on them and get one back.
Well, you think you can get one, but I mean, what about the idea of having an extensible list? And if you want to get a length 10, we say extensible list. Well, if you say take, one of the questions is, if you say take range of infinity, 5, do you get back an extensible list, or do you get back an ordinary list? Do you get back range?
List is what you're calling this. I think you should get back an extensible list, and you should only, it's like a sparse array.
Okay, that range of infinity gives an extensible list, and that this gives back an extensible list.
Yeah.
Okay. Or an implicit list, or whatever we want to call it. What should we call it?
I mean, I think the real thing it is lazy.
I just am not a big fan of that name. But okay, we can have that for now. Okay, so assuming we have a function called lazy list, what else do we need? I mean, how would we get?
Again, though, I mean, things like array and range, you'd probably need to have.
Well, why not just say range of infinity, and then
because you might want to, again, because you might, you can have finite lazy lists, and so you might, unless you want to restrict range to only constructing infinite ones, and then you don't really have any good way to construct finite ones.
Well, you do a take on a range. If it's a very minority case, a take on a range seems not completely crazy.
I guess so.
It's less clear when you have a two-dimensional one. I don't quite know how that would work. I mean, what happens if you have a triangular array? And I guess there's ways to handle that as well.
Yeah, with laziness, you really never know what shape it is, unless it's expanded.
Right. Yeah, hold on, guys. I'll be right back. Just a second. I'm sorry, I'm back. Okay, where were we? So the question here is, can there be a single lazy thing where all these other functions have up values relative to that thing? And I believe
yeah.
Go ahead.
I was just saying yes, as long as the inputs, look different, right? You can even actually define an up value.
Yeah. Well, okay, but Nick, the technology you have, would it work with this?
Well, it kind of does already. It's like, so that I have a separate functions that work with lazies doesn't matter. It's just, we can just dispatch sub-values to those.
Okay, fine.
There's
Okay.
also a question that the actual head cons can also have flat attributes, which I also trying to do.
Well, wait a minute. Can we be specific? We're talking about lazy list. Do we also think there's a lazy tree that's needed?
Yeah, the trees and also the lists. There may be two versions of list with flat and without flat attribute.
Why? Why?
Because I think having a cons that have a flat attribute is also can be useful.
For what?
The trees, I think, are a totally different thing. I mean, I think that's for representing data that is shaped like a tree. I mean, it's very natural to do also. I mean, you can just make something that's like lazy tree, has the same argument structure as tree, and basically works in the same way. And make a lazy tree. But I'm not sure we know enough about how that would work, what that would be used for. So,
I would say we have basically lazy tree. It's called nest tree, except the only operation that's supported is root tree. Like you can construct so many levels. But the basic idea of nest tree is that you have a function that gives you the children and you have a function that gives you the data. And using those,
how do I do that? How do I make that?
So the first argument is the function that gives a list of children. So just do like 2 slot, whatever.
Okay.
Mm-hmm. And then the second argument is the initial expression. So like 1. The third argument is the number of levels. And then the fourth argument is the data.
At each level.
Do like comma H.
Right.
So
but
right,
I guess
the first
point is
and the fourth
represents
argument.
Sorry,
the first and the fourth arguments correspond to tree children and tree data. And that gives you a lazy description of a tree. And what nest tree does is samples that out to 3 levels.
Right. But I guess the keyword is samples. Right. I mean, like for example, with the Athena's project, the point was like she made exactly the same thing where it's sort of an infinite, I forget what it was called, but it was sort of like an infinite nest tree where it's the same thing, except you don't say 3. You just don't tell it how big to make it. But
same thing.
You could run operations
these same arguments just without an in. And then I could imagine tree map and tree extract just working on that, because the tree extract code, like right now, has to do things like extract the children. Lazy in that context would just mean wait until that moment to apply that function.
And presumably wouldn't have to generate the whole tree in order to do so. And also you'd be able to, have that, symbolic lazy thing. You could map over it, you could do whatever and so on. I mean, in many ways, it's not quite, it's not as useful, I think, as the list case, in part because with the tree case, there aren't as many structure transforming operations. Like with lists, you can do super useful stuff by running, for example, select, because then until you run something like select, if you're just kind of calling map and replace and whatever, these functions where fundamentally all the arguments stay in the same spot, you don't need to generate the first n arguments, first n minus 1 arguments in order to get the nth. It's only when you start calling things like select that you have to do things like that. But with tree, it seems like there aren't really as many operations like select, and so the laziness isn't as valuable. And also, I think I think less lazy trees as an idea has just come up a lot less, and so I'm not sure
Well, okay.
One application I have in mind is it would allow for so for example, you could take XML and convert it into a tree using expression tree, do operations, and then convert back into XML using tree expression. If you had the lazy version, you could just do the operations from XML to XML without having to construct the tree while still doing all of the effective tree operations.
Okay, but a different point is that this question about, you might end up with the depth first branching down the tree being wanting to be constructed and other ones not. Just like for nest graph, we have exactly this issue. We could make an infinite nest graph as well. But that's more complicated because the evaluation front is not so obvious. Does that make sense? I mean, like if I could have an infinite combinator expression.
Right. Yep.
I mean, there's clearly value in being able to do operations on these infinite combinator expressions, for example. But I agree, the first step here is lazy list, probably. So just to be clear, the way this would work is that, I mean, one possibility, what does this do right now?
Seems fair.
Yeah. So, I mean, that could generate an extensible list, lazy list, whatever.
But I think in the same ways with sparse arrays, I think it should be its own, because one, you might want finite ones, but also because I think that, right. I mean, as with sparse arrays, it has its own constructors, and only if you specifically ask for, very few functions make this sort of decision where they say, oh, I'm going to implicitly, I'm going to guess based on the structure of my arguments that in this case, you really want a sparse array here.
How many lazy constructors are you proposing to have?
Probably like one, maybe two. I mean, lazy range for sure. And then otherwise nest list, but nest list could probably be repurposed to do it anyway by just having a 2-argument form.
But so what about lazy table? Or lazy nest list? How do you get
I guess table will be another fine one, and maybe I mean, array. So,
but what about?
I think there's a handful. It's quite a small number. Like there are a lot of operations, but there are many fewer.
Constructors.
Yeah, and a lot of the constructors, again, like a lot of those, like nest list and fixed point list and so on. Those are ones where the argument structure would be different if you had an infinite one. And where there's really no reason, well, yeah.
So what are you suggesting? Are you suggesting that 2-argument nest list does the infinite case, or are you suggesting that instead there's a lazy nest list?
Well, I'm thinking about it. I mean, the argument for right. I mean, for example, if we're taking seriously what about the finite case, then that would be an argument for having the explicit lazy nest list. But I'm not really sure how much the finite.
What would it even mean? I mean, so let's say we have this case. What would that mean? What would it do?
I mean, we're return a lazy list of length 10 to the 10.
Which you could reverse, for example.
I'm not sure reverse would be a supported operation for lazy lists, but at least this kind of lazy list.
For a finite one, you could do the reversal.
You could, but I think you really can't for an infinite one, so I'm not sure it's worth supporting the operation.
Okay. What difference does it make then to have a finite one? I mean, I can get total, presumably, on a finite one as well.
Yeah, I mean, the reason, I mean, I think part of the reason why finite ones are useful is for doing like indexing, like for example, running take.
Why is that? Why is the finiteness useful for that?
Well, it just makes it, I mean, if you have it so that take, converts it into a list, I mean, you end up with this sort of weird situation with, right, here would be an example, right? So one of the standard ways of implementing Fibonacci, this is like a classic piece of Haskell code, which is you can make this self-referential Fibonacci where you basically say, I think there's even an example on the notebook on the right. If you scroll down just a little bit, it's fib2 equals cons of one, map thread plus fib2 and rest of fib2. Okay, so basically you're adding, the thing equals itself plus itself shifted by 1 because of the rest.
Yes.
So should rest return an infinite list, or should it return a quote unquote finite one?
It should return an infinite list.
It should return an infinite one, right? But rest is kind of like an indexing operation, just like take. And it should be possible to write take, 2 to infinity as well, and have a similar thing happen. But so if 2 to infinity returns an infinite list, or whatever, then I think, or if rest returns an infinite list, then I think take, 10 should also return the same structure of thing. It shouldn't be kind of thinking about it and deciding, well, in this case, the thing could be unbounded, so I'm going to return a different type, because it's kind of a non-trivial thing to work out in what cases it's going to be unbounded and what cases it's not.
And you're claiming you could probably make it undecidable whether it's unbounded or not.
I'm not sure if you really could, but I just think it becomes hard to reason about, and you're going to end up with weird, unexpected stuff where, I have this input n, and when n is greater than 10, it returns an infinite thing, and when it's less than 10, it returns a finite one. And it's like,
I don't understand this. I don't understand. What's the difference between lazy range of, 0, 10 and range of 0, 10, other than that lazy range won't actually generate anything in memory?
No, it'll generate a cons list or lazy list instead of range, which generates a list. I mean, it's the same thing as saying, like, what's the difference between list 1, 2, 3 and sparse array of 1, 2, 3?
Right.
It's
So
like,
you're saying
they are
normal
the same
of the
thing, but
lazy range will actually give the explicit list.
Yes, definitely.
And again, explain to me again why this limiter is relevant, other than that. I mean, what functionally is the difference between, you're saying.
So the limiter is relevant for maybe 2 reasons. One reason is this thing about indexing that I think, if you can't have finite ones, then indexing has to sometimes return a finite one and sometimes return an infinite one, which can lead to all kinds of weirdness. The other issue is that I think there might be cases where you want to have it be finite but lazy. So an example would be, this is more of a programming example where I'm not sure this is the best suited application, but suppose I'm reading from a file. The file is finite, but I want to do it lazily because I want to kind of be streaming in some way.
Mm-hmm.
It's not infinite.
Yeah, okay. Okay, but fine. So you could then say length of the finite.
Right. Although length is again kind of well.
No, but if you're going to have finite ones, you want that. And length should return infinity. In the case where it's an infinite list.
Well, but it doesn't. Okay. Well, that's super undecidable whether it's it can never return infinity. That's undecidable. Even the saying, oh, the length is 10, that's also undecidable.
Well, for a general constructor function.
Yeah.
I think we should try doing this with a single lazy list construction.
It's like, just think about something like, you make a lazy range and you map primes over it and you ask for length. It's like, it clearly can't say infinity. Or you select prime q.
Why isn't there still an infinite number of primes? If I select twin primes, then it's kind of screwed.
Well, no, but even yes, there is infinite number of primes, but it cannot possibly know that. I mean, it can't possibly just look at your program with a prime q in it and say, oh, well, there's infinitely many primes, so.
I mean, we do know that. Reduce knows that, for example. Reduce knows that infinite many primes.
But again, this is coming back to the different kinds of infinite lists you might have. I mean, this is the thing that we talked about in Athena's project, was basically if we had if we had a very different representation of infinite lists, then it might make sense, like the thing where, you have a function where you give it a position and it gives you the value. Then it might make sense to, to do sort of mathematical reasoning about it like that. But I think given this representation of infinite stuff or lazy stuff, I don't think that makes much sense. It's really hard to convert between select of lazy range of prime q and a mathematical expression, and I don't think you could possibly do it reliably. But with another representation, you could, which is another reason why I don't think any of these should really be in system, because it's really not. There's no.
Right. So one path here that we have is building a lazy lists packlet, which is kind of what Nick has already done here. Look at that. Okay, in which there are tons of lazy operations. And
yeah, I think that's great. Yeah. I like the graphic too.
Huh.
You can open a guide, have like a little bit more information there.
What does all true do?
It's a thing for
No. Lazy all true. I know what all true does. But does lazy all true consume a lazy list?
Yeah.
I assume it's a theorem of some kind. Is that true?
So does it just...
I use it actually in the prime definition. You can just on the left.
So out of curiosity, I mean, do you? So first of all, do you have finite lazy lists, or do you only use infinite ones?
Yeah, I also have finite and infinite. Doesn't matter.
Oh, okay. So all true can. I'm just wondering if all true can ever return false, or sorry, can ever return true. But if you have finite ones, then it can. So yeah.
Yeah.
But by the way, do you know if do you do something special with recursion limit? Because I know there were issues that I had where it seemed kind of unavoidable, where you can construct things where
you can
recursion limit.
You can circumvent it a little bit. Your normal would just basically append to an empty list until it can, so that there is no actual recursion. You just unwrap, unpeel the lazy structure slowly, one by one, without recursing.
I tried to do something like that, but it still got mad at me. But maybe I was just doing it wrong. And I don't remember the details because it was like years ago. But yeah.
Okay. I basically made this, and even if you have an infinite lazy list, if you make normal of it, it will think indefinitely. But if you abort it, it will just spit out up to the point it already computed the normal list.
Wow. Okay. Given this, so in this strategy, where we're just making a packlet to do this, well, then you're about to describe how it's useful for your pattern stuff, but presumably we can make lazy nest graph from this as well, can't we?
Well, no, I'm not sure how yet. I see how you have a tree, but how the graph would be different from a tree or something like that. You have just a nested, basically, if you have a lazy list, you have a arbitrary nested list of lazy lists and so on. And you can just traverse it arbitrarily. And graph would be just when you have some kind of equivalence between things.
Mm-hmm.
Unless it's just some generator of edges, which is just a lazy list again.
But that's turning a graph into a DAG, basically.
Yeah.
And I think that, okay, let's look at your pattern matching stuff. So what is this doing? What is pattern substitutions?
This is what I want to return a lazy structure or generator of things. It's like this returns some kind of lazy thing that you can traverse, and it contains two different heads as a sum and product. We already looked at it last time.
Yeah, we looked at this.
So now just outputs all of the matches or whatever number you can provide. But if you just return like a generator, I could just traverse it, and because pattern match is inherently recursive, I can use it in the definition of all the pattern objects easily. If I just want a single result, I can just ask it for a single result, and it would do it naturally and efficiently without traversing every possible combination of matches and so on.
Well, so I mean, from a practical point of view for users, this can be an opaque box. You don't even know how far the laziness has gone. That is, this would return, rather than returning this, you just return a summary box here.
Yeah, which is just a lazy generator. Yep.
Internally, that's what it can be.
Yep.
But now, so that would represent, that thing would return something that represents all substitutions with this thing on that.
Yeah.
Why is it called pattern substitution? Why isn't it called matches? Because then the substitution bindings is essentially a property of the matches. What other functions?
Maybe it could have called matches. I don't know. I don't remember why I called it that.
You have a guide here as well.
It's just the function of, for example, substitution apply that takes this substitution and applies it to a pattern to reconstruct an original expression that it matched against. And if you apply a match, and it doesn't make sense to apply a match to a pattern. I don't know. Substitution basically is an idea that holds every substitution and a binding. Binding is a kind of special version of substitution.
Okay, I'm confused here. The big picture of what we're doing here is we're defining for a replacement for a, we're saying we've got an expression, we are going to apply a replacement based on some pattern. What are all the possible ways in which the pattern can match? It is the case that in doing a substitution, you never need to know about the right-hand side to determine whether the pattern will match. Is that true or not true? I remember there were some weird cases back in the day, which we may have cauterized, that had to do with like default arguments and things, where there were cases where you simply couldn't determine the right-hand side, where there was a nominal match, but it couldn't determine the right-hand side. I'm saying, so we just decided to make those not match. So we never had the issue of having the undetermined right-hand side.
I don't think it's the issue now.
Okay.
Well, aware it.
Okay. But so what's the big picture of what will be done here? So, I mean, you have many substitution bindings, okay. Well, these are interesting, but I mean, okay, so what, go ahead.
Well, one of the things I also wanted to achieve with the pattern things is to be able to easily make custom patterns. It's like, what if a user wants to have it like his own pattern?
Sorry, I don't understand. What? I mean, we
It's
have
like,
go ahead.
I just want to like make it possible to make an own pattern things easily. And I don't know. And basically how we use it is just to make a sub value for your pattern object for pattern substitutions, so that it produces this generator.
Do we have a single example of where you'd want to do this?
Or I don't have it, but I have plans. Like, for example, I wanted some kind of pattern that is a dual to alternatives in a way, or not a dual to alternatives. So it's like very close to options, but for arbitrary things. Options pattern basically takes a list of patterns that you wanna match against some subset of it, right? But it works for rules, and then kind of the same pattern, but just matches against subset of rules, subset of expressions, whatever. So if you want to define it, you basically make your pattern substitutions for this new object.
So
it's a little bit like repeated of alternatives, kind of, or no, because you can't have repeats or something.
Well, I mean, a naive case would be something like double blank blank G. That is everything, or blank blank. I mean, the the options pattern must be very similar to double blank rule.
Well, it's not, because you can have arbitrarily nested lists around it and so on. Also be triple blank, but yeah.
Okay. But so I'm still trying to understand here. What was the thing that we were trying to solve originally? We want to be able to take, original objective is, we're trying to be able to generalize things like trace graph to the multi-computational case. So what you have here is something that is the core of a replace list all the way down. But as we've discussed previously, I mean, for the pattern matcher, it's a multi-output function. For most built-in functions, they're not multi-output.
Yeah.
But okay, I mean, the way we make, so, multi-wayness of typical evaluations can be achieved by just by allowing all possible evaluation orders. Does that make sense?
Yeah, basically you can evaluate any unheld sub-expression in any
Yes.
order.
Or at least, if I have this, I want a transformation where this has been made into FXBCD, FAXCD, and so on. Right? So, I mean, that's the difference between, if we imagine sort of physics project type stuff, that's the difference between you take the whole of the, the whole hypergraph and you rewrite it all at once versus you can rewrite any subpart anytime you want. By the way, what happened to your compile everything to hypergraphs concept, Nick?
No, it's there. It's not developed much further. I have some like general causal graphs, and basically that's it. That's enough.
But now also a summer school project though of compiling a whole bunch of stuff.
Yes.
Yeah. Uti had this project, compiling different computations.
How far did that get?
I mean, I think he had DFAs, NFAs, Turing machines, non-deterministic Turing machines, some like tags, register machines or something. And then he even had some, I think he had some very basic kind of interpreted Lisp-like language or something that he compiled to.
Yeah, there's some kind of complicated language, basically a small version of assembler. There was a bunch of instructions.
Okay. So what we learn from that is a way of making everything be able to have a meaningful causal graph, because we've broken things down to the eames, as we might say in Ruliad speak. We've successfully broken down everything into eames, and therefore, because we can trace eames, we can know what the causal graph is.
Yeah.
And so,
can I ask, what is an eame?
It's an atom of existence. So it's the lowest level thing. In the model of space that we have, there are atoms of space that have relations that are defined by the hypergraph. So an EAM is a generalization of that idea. It's an atom of existence. In the notion of atoms in computer data structures, it is the ultimate such atom. And the only thing that you can say about an EAM is that it's different from all other EAMs.
And that it exists.
And
Further
that
port-
yeah.
It's just a fundamental unit of computation that we tend to use when we're speaking globally about computations, like when we do multi-computation, for instance.
Right. So this is basically compiling down to EAMs in a way that, because Wolfram language, for example, has the notion of functions with arguments, that's higher level than EAMs. It is okay. Traditional mathematical logic and mathematical notation has the idea of variables and quantifiers and things like that. One could compile all of that stuff down into EAMs, into some kind of uniform representation layer. And I think what we're talking about is compiling Wolfram language stuff, which also has, like traditional axiomatic formulations in mathematical logic, has a certain amount more structure than the pure sort of emic structure. Right. It's in a sense, something like Lisp perhaps would have slightly less structure. And the trade-off is the less structure you have, the more incomprehensible it is to humans. But I think that's the idea, is to compile it to something completely uniform. I mean, we could as well perhaps compile to Turing machines, but I think that hypergraphs are more convenient than Turing machines. Do people agree with this characterization?
Yeah, hypergraph are ubiquitous.
Is what?
They're ubiquitous. You can convert anything to them very easily.
Right. You can convert anything to Turing machines. It's rather hard in many cases.
Yeah, it's much more powerful.
Okay, but so, for example, in Ian's trace graph stuff, we could represent every expression as a hypergraph. We can represent every variable that is defined through the symbol table as a shared atom of existence in this hypergraph. Is that a true statement?
Yeah, right. Yeah. Basically, a variable is it's kind of, it depends where you have this atom EAM as a part of a rule or a part of a hypergraph itself. So we kind of have to distinguish between patterns, variables, and just expressions.
Yes. Well, except in the mathematics project, we found a way to merge those two things together. I mean, you can either put a little bit more sophistication into the laws of inference, or you can say what you just said.
Oh, yeah, basically, you can convert an expression or a pattern to a hypergraph.
Yes. Okay, but were you to convert the expressions in Ian's trace graph to hypergraphs, then we can immediately produce a causal graph, correct? Just by tracing EAMs.
Yeah, correct.
And it is slightly unclear how we produce a causal graph from the Wolfram language expressions. Also a true statement?
You mean directly or through the hypergraph compilation?
No, directly.
Yeah, that's kind of unclear.
Right. Now, there might be more than one way to compile a Wolfram language expression into hypergraphs.
Well, it depends how it also represented internally. If you just have all the symbols in the expression mapped to some internal memory, that basically memory addresses is like an EAM.
Yes. Well, and the only thing that's in there is a bunch of pointers.
Yeah. So you just trace the pointers. It's the same as tracing EAMs.
Yes. But again, once we've said that, one of the key things is that because everything has a place, the causality of things is clear. Because there's no notion of, you can't make a copy of a thing. It either is at the same place or it doesn't, or it isn't the same thing.
Right.
Right? That's why there's a well-defined causality. I mean, the difficulty for causality usually is that you can end up, I mean, this is a standard issue. I mean, you can end up with right. I mean, this is a famous case, right? If we do the following thing, if we say XX equals n of blah, 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 comma, 50. Okay, actually, and now I say XX minus XX. Am I doing the right thing? Then the whole point is that those are, how do I do this? There's a way of doing this where basically the question of whether it's the same number, it can be the number that is represented the same way with n, but it isn't the same number. Like, is this making any sense to anybody? Let me say it again. In numerical round-off, right, we could have two numbers that have the same representation, but they come from two completely different places. So if you subtract them, the correct thing to do is to give a number that is of order their precision. Of order the 10 to the minus whatever their precision is. If, on the other hand, both those numbers really did come from the same place, when you subtract them, you should get 0, because you know they're the same.
Yeah.
Right. So this question about absent the idea, so the whole point is there is no meaningful sense with your EAMS with addresses. There is no meaningful, numbers couldn't be the same unless they were in the same place. Does that make sense?
Sure.
In other words, there is no, okay, in a world where everything is EAMS, there are no literals. Right? There's no string literals, there's no number literals. They're all just, the 2, there is a unique 2 in the world. Am I right?
They have to be unique.
Right. And once they're unique, causality is easy to trace.
Yeah, I agree with this.
So that's really the main thing we're achieving by emifying, aka hypergraphifying everything, is that then we have squashed out any literals. But the overall objective of this, again, was, right now, the only multi-weighing, okay, there are two kinds of multi-weighing that I can see in Ian's trace graph. One is whenever there's pattern matching, you could match in all possible ways. And the other is you can use all possible evaluation orders. Am I making sense? I mean, there are other things which, in principle, functions that right now return one argument could be one value could be redefined to return multiple values.
Yeah, like x can have multiple own values.
Yes, and this is where the multi concept comes in. And right now, the only way of multiplying things, so to speak, as opposed to multifying, is through the pattern matcher. Or, what's that?
Multiple values. Basically, even like there could be multiple down values that match the pattern, and then the pattern itself can match multiple results.
Yes. Okay. How does multiness arise? Okay, so thing number one, multiple pattern matching, multiple pattern matches.
Right. Although if you're talking about things like down values, I would argue that, I mean, there is down values are not multi-way because there's a way of choosing which is the most specific one. Right.
If there is, there might not be.
Well, on the off chance, I mean, first of all, just on a practical level, you'd like to be able to do multi-way things. Even, you might not want to have to guarantee that all the down values that you want to sort of non-deterministically pick between are exactly the same specificity, because that would be very annoying and people don't know how that works. But yeah.
Yeah, that's practically how we program. We have to always order the down values in order to return the desired result.
I'm just saying, obviously it makes sense to talk about basically the replace list like idea, but I think that it's, it's not the same thing as just down values, because down values do have a canonical way of choosing one.
Well, so does pattern matching.
Right, but we're sort of ripping apart the concept of a down value, I think, by doing that. Like down values basically call replace, and the other thing
I understand.
is that,
this is a multi-down value. This is not a down value. This would be.
But also, if you have down values, if you have down values of existing functions, it often makes no sense to apply them non-deterministically. I mean,
I agree.
Nothing else, you might have the fall through error case is defined or something. So
right,
that's
but I mean,
practical point.
Look, evaluation orders for sub-expressions might also not make sense. Like the sub-expression could be, compound expression, and then it would absolutely not make sense to do things in different orders. But so, in other words, each of these has to be done with care.
Yeah, I'm just saying, I'm not sure it makes sense to literally get the multiness by looking at down values of f.
Well, I don't think any of these make sense. I mean, look, there are plenty of pieces of code where multi-pattern matches will give wrong answers. The non-leading pattern match will be the wrong answer. Just like the non-leading evaluation order will be the wrong answer. I think this is essentially what one might picturesquely call quantizing code. Not just going down the primary classical path, but allowing all possible paths. And I agree that much code cannot be quantized without it just blowing up in all kinds of crazy ways. But the thing I keep on saying, for Nick and everybody else's benefit, is we need these functions that are the things that observe interesting properties of quantized code, of multi-way code. Find replace path, for instance. And Nick, can you explain? Okay, so there are these ways of generating multiness, of which probably the cleanest is this pattern matching based one.
You can also have an explicit multiness. So if you have a rule that explicitly returns multiple results.
Yeah, okay. Okay, so then there's, okay, right. i.e. multi. That's the explicit version. And by the way, the pattern matcher could return a multi. Any of these things could return a multi.
Yeah.
Right. And then the question of, do you have multis implemented? Because one obvious question is equivalencing for multis. Like, for example, if a multi has multiple graphs in it, does it do graph isomorphism?
Well, it should be just graph isomorphism. It should also compare the actual values, right? What's the point just comparing graphs?
Maybe so. But I think it would be good. Did you implement multi yet? I mean, look, it seems to me that we really need, okay, multiple pattern matches. We need a version of replace. We need something that's called essentially replace multi. But instead of returning a list, returns a multi. And then, I think replace repeated multi is basically the evaluator, give or take.
Yeah. Well, my multi kind of worked. What it was capable of is if you provided an expression, it just searches for all the down values and it tries to apply all of them.
Okay, but so that's one form of multiness.
Yeah, well, also you can make an explicit list of rules or just a list of explicit values, and you can combine them.
Okay, but
that's not enough. It's
in the end, we're going to generate a multi, which will probably be lazy, and then we're going to ask certain things about the multi, just like we're asking certain things about lazy lists. Except that in the case of the multi, one of the things we want to ask is the proof path.
Yeah, multi is an example of a lazy generator. That's a nice analogy.
Oh, which generator?
Lazy generator. You can.
Yes. Yes, but I mean, my point is that what we want to extract from a multi, in a lazy generator, one of the things that's there is information about history, or potentially there. And in a multi, we often want that information about history because it's the proof, basically.
Right. So, for example, multi-object that I have a property that first of all returns like edges, basically, that you would use in a causal graph or a states graph. And you can just run, instead of producing edges, you can just run it and produce a next multi-object that just contains all the next hypersurface, basically.
Yes, right. So every multi defines a hypersurface.
Yeah.
And what's not totally obvious is, given one multi, as you evolve that multi, you have to define what foliation you're going to use to say which hypersurface you get next.
Well, if multi, yeah, basically, right. Because if you just apply all the possible results, all the possible rules that it contains with all the possible values, what would you pick for your next hypersurface?
Exactly. Exactly.
So you have to put the other ones somewhere. I think multi always have some canonical order, canonical foliation, basically, because it always have just apply once, whatever rule, whatever pattern matching, just apply it once.
But where? Which one do you do once? But what if they overlap?
Or you just anyway, if they overlap, you try all possible overlaps. That's all the sources of multiness you can try, and you can try it all together. And that will just provide the new hypersurface. There's no kind of ambiguity where to turn. You can prune them afterwards.
Yeah, okay.
But nothing else, I think.
Let's try and so I think this description of types of multiness is useful because some of them are more controlled than others.
Yeah.
I mean, let's try to get implementations of some of this. But then again, I keep on asking for the thing that takes out of a multi the things we care about. Like, for example, given a set of rules, how do we apply these rules so that we get a result with certain characteristics, if it's possible? Right. All right. We should probably wrap up here. Kind of late for something else. We're making progress here, guys. We're making progress. And Nick, I mean, do you feel like you have a definite direction of how to go multi with these things?
Well, now I see it's just okay. After I play around with laziness, because I still think my kind of view of it is completely different. I would treat, because I still want this like to work some functions that work on arbitrary held symbols and so on.
Oh, fine. I mean, look, I think we're giving up for now on the idea of a single point of laziness, so to speak, and we're agreeing that there should be a whole packlet's worth of stuff.
Yeah.
So I think what you're building is in fine alignment with that. Now, what was the other thing you were saying?
And then this multi-object can be viewed as one of the generators of lazy graph. And then I will look at what can be done with it.
Yes.
Like all the traversals of graphs can be lazified, but when your lazy object is a multi something. Basically.
Indeed, because every slice of the graph is a multi.
Yeah.
Although I claim you actually need to know in that, well, I mean, it's a question of how the graph is traversed. And maybe we start with DAGs.
Well, that's what would mean to lazify functions. So if you have breadth first scan and depth first scan, your lazy versions would actually traverse this multi thing in the corresponding order.
Yes, I mean, well, the lazy thing doesn't define the order. It's when you actually start evaluating the lazy thing that you have to define the order.
Yeah, so the functions define how they would use this generating object.
Well, the multi could be thought of as like an intermediate state in a multi-way system. A multi is laid out in branch hill space. And that's another useful way to look at it, perhaps. Whereas a list, or even a lazy list, might be laid out in list space, so to speak, in one-dimensional list space. A multi is laid out in branch hill space.
Yeah. So basically, multi can contain lazy lists inside of it. So like the result of that generating values for multi can be just represented by lazy list. And then you can just pick first result of any lazy list that would be a depth first order. If you just traverse all the lazy list on the hypersurface, that would be a breadth first.
Sure. Well, and it's a lazy list in the sense that there is a canonical ordering of the eames in this, or whatever they are, of the expressions that you get inside the multi. In the slice of the graph, assuming that you've got an index graph and you've labeled every node of the graph, then I agree with you that it's a lazy list of elements that represent one current kind of orthogonal to time hypersurface. Does that make sense?
Yeah, and you can the outside functions for multi can control the order in the lazy list, how they're generated. So multi contains all the rules and all the meta rules, how to apply those in any different order that you would want to ask of it.
That's fine. I mean, if you want to do it that way, yeah, right. That's fine. The multi already, I mean, the multi, by being a hypersurface, knows what kind of a hypersurface it was and how it was derived, is what you're saying.
Well,
I can imagine a disembodied generator of the graph that does not yet have foliation information.
I don't think like multi necessarily should contain the history. It's whatever uses it and traverses it should contain it.
Okay. Well, again, I really think we need to do this exercise where we've got the space-like multi-type thing, you've got a time-like path, We've got to be able to extract those things. Right? We've got to be able to extract the list of multis that will be essentially, well, okay, we got the list of multis, which are the contents of the hypersurfaces, the contents of the anti-chains. We've also got the branchial graph of any multi, right? Any multi should have a branchial graph, I claim.
Well, yeah, okay. If it knows the history of how it was applied, produced, how it was produced.
Yes. And but I mean, so I think what needs to be done is we've got to define for those different sources of multiness how to generate the multis yeah, and then not only how to generate the multis, but also how to trace things like the proof path. Now, maybe those traces have to be from things like trace graph. Maybe you have to have maybe there's an evaluation process that gives you a series of multis, and you have to explicitly trace to know the history of the multis. See what I'm saying? I mean, like in standard Wolfram language, it's an answers only system. It does not give you a trace of how it got there. For that, you need to use trace or trace graph or whatever.
Yeah, I think it's enough for multi to just contain the output results and the events that produce them, or just the events basically. If the multi was a container not of expression states, but a container for events. So
then you are storing history in the multi.
Yeah, but only one level. So it's like
why wasn't only the one level? Because it goes back to another multi.
Oh, I don't think you need to like store all of them, right? It's like initial multi just contains all the initial states with some initial event that produced them. If you generate a new multi object, it just contains all the events that can arrive.
So it's kind of like a linked list of multis. Every multi refers to a previous multi.
Yeah, if you just you can make a linked list of multis. It's one of the operations they can do. Yeah.
Right. So it's like time as a linked list. Computational irreducibility implies that time is a linked list in some sense.
Yeah. Basically, multi is also a spatial hypersurface, right?
Yes.
If you just a container for events.
For the most recent events. I mean, you could represent it by the previous multi plus a bunch of events. Or in principle, you could represent it by a very distant past multi plus a bunch of events. I think you need to implement some of these. I think you need to implement multi. Plus, for goodness sake, let's implement some of these operations that we've so long talked about, like find, replace, path. On multis constructed by some of these methods.
Okay.
I mean, what I find interesting conceptually here is, we have classical computation, which is the one pathway of doing things. In sort of the texture of how one gets to quantum mechanics, involving quotes, quantization, which is, the texture of what we have to do here is very similar. Right? We add all these possible paths, and then we have equivalencing between paths. Which is its own operation. And let's see, when we've got these different paths, yeah, I mean, I'm making the guess that something like destructive interference. Okay, here's a bizarre claim. Okay, let's say you have an error case in a collection of down values. As soon as you go quantum, you have the possibility of exciting that error case, even though just because it's one of the possible, unless you lock the error case by having, by saying only if this happens, do you do it, as opposed to just saying it's one of the gang, one of the collection, but you wouldn't normally get to it in the classical operations.
Sure. Yeah.
Then, in a sense, the error case is a piece of probability, so to speak, a piece of amplitude that sort of escapes into the goes off into the sunset, as opposed to most operations that stay in this region that is the one that you are seriously going to observe. As opposed to going off into the sunset with this weird case that you're not interested in. Yeah, there's going to be some analogy here.
No, the only analogy I think it's okay. Multi-way system is, if you want to interpret quantum mechanics, is mostly many world interpretation similar, right? So as soon as you have events or rule applications that overlap, that's when the world split.
Yeah.
And you define your measurement as some kind of rule that can exist on both branches.
Right, but the key difference between many worlds and this is that we imagine that the brain is also many-worlded. Right? In other words, the observer is part of the system. The observer is not just sitting on one branch.
Yeah, it's a part of the system, so that the similar rule that has the observer and the thing that the observer measures can be applied in both branches. And because branches are different, there are different results.
Yeah. Yeah, but the observer spans many branches. The observer is quite big in branchial space.
Right, yeah. Basically, IMS, that part of an observer contained in both branches. And if the rule matches IM of an observer and IM of a system, branches measurement on different branches have different results. And if the system contains some kind of phase,
yes,
that would can be destructively interfere. So
yes. All right, we're getting there. This is more to do. Okay, I think we have a path here, and
several.
Right. Okay. Good stuff. Well, thanks, and to be continued. This is very exciting stuff, in my opinion, and we're we're really making progress, I think. And Nick, we really need to. Yeah, I mean, I'm convinced you've done something reasonable in this implementation of the lazy Packlet, which should make it to the Packlet repository. And let's see some multi stuff here. Evaluation orders and observers are going to need to be made computable here, and that I think is what we're going to run into next. We already talked about some of the evaluation order stuff, but with more to come. Okay, to be continued. All right. Thanks, guys. See you later.